Okay, so firstly, thank you very much for the invitation and thank you for the organizers. So we will present our recent work today, quantifying uncertainties in the axion flux and their impact on determining axion model parameters. This was work done together with my PhD supervisor, Joerg Jaeckel, and Sebastian, who will speak later as well. So the motivation to do this was that there is renewed attention to solar axions and ALPS. Firstly, from the experimental side, so baby IAXO is being built at the moment, and it will be the first helioscope to explore the QCD axion band. But also last year, there was the Xenon one-ton access, and the Xenon collaboration also considered the possibility that they might have detected solar axions. There's also a bit of new attention to various solar production processes. For example, there were a series of papers on the plasmon conversion in large-scale solar magnetic fields, but also there's some interest in axion production in atomic transitions and how one could measure the chemical composition of the sun from that. So that also brings me to the final motivation. When we want to detect solar axions, we also want to learn about the axion itself. So for instance, we want to determine the mass of the axion or its couplings. And we might also want to do some axion astronomy, so determine solar physics from a solar axion measurement. This could include chemical composition, metallicity, or the magnetic field inside the sun. So for all of this, it is very important, how well do we actually know the flux? So how good is our prediction? And a more specific question that we ask ourselves is, can we actually distinguish different QCD axion models? So for all of that, we started this project and we wanted to revisit, check, and implement the solar axion flux calculations, or implement it in a easy to use code. And then we want to estimate the statistical and the systematic uncertainties of this prediction. And finally, want to investigate a bit the relevance of these uncertainties for the axion detection and for parameter measurements, and even for solar probes with axions. So let's get started with all the processes that might be relevant here. So we are considering an axion-like particle with CP conserving electron and photon couplings. So we just have a standard kinetic term, a mass term, and these couplings to photons here in blue and to electrons in green. What we're not including are nucleon couplings. This is because typically interactions of the axion with nucleons generate axions at much larger energy. So this can be well separated from all the effects that we are considering here. And we're also not considering any CP violating interactions that in general ALP might also include. And another simplification that we're doing is that we are assuming the mass of the axion to be much smaller than the energy in the sun, which is at the core where most axions are produced, of the order of kilo electron volt. However, for the detection, we don't have to assume that the axion is massless, but we're just producing ultra-relativistic axions. Now, these processes that we illustrate here by these diagrams can be split into two categories. Firstly, the ones here in the blue box, which are based on the coupling to photons, and the one in the green box are based on couplings to electrons. So the blue ones, the most famous one is the Primakov production, which is just a photon scattering of either an electron or a charged nucleus, and thereby generating an axion. And the other one is this plasmon conversion in the large scale magnetic field. So this is just the background magnetic field in the sun. And inside this magnetic field, plasmon can also convert into an axion. This can both happen for longitudinal and transversal modes. I will mention this in a bit more detail later. And then there are all these other processes where axions couple to electrons. This is also, the combination of all of these is often called the ABC flux, which stands for atomic transitions. These are the ones on the bottom here. Bremsstrahlung, this is on the right, and also the Compton effect, therefore ABC flux. Now, to calculate the resulting fluxes, we can rely on work that was carried out by many people in the last decades. For instance, the Primakov calculation, we can use the calculation by Georg, which already included charge screening, and we also include the full plasmon dispersion relation. For the plasmon conversion, there was a lot of work done last year, and this includes the resonant conversion of longitudinal and the non-resonant conversion of transversal modes. Because this might be a bit unfamiliar to many, because this is relatively new, I will go into a bit more detail here and already show you the resulting flux for a second. So as I already mentioned, there are resonances in the production rate of plasmons, but the resonance conditions are different for longitudinal and transversal modes. So for longitudinal modes, a resonance occurs when the energy of the emitted axion is equal to the plasma frequency in the sun. And the plasma frequency in the core is of the order of a few hundred electron volts, and therefore we generate this peak here in blue. The blue lines are longitudinal plasmon fluxes, and this is a resonance peak. This band is so wide because the magnetic field inside the sun is not very well known, and actually the normalization, so just the absolute power of the magnetic field, can differ by a factor of 10, which results in a factor of more than 200 in the axion flux. So this flux is relatively poorly known, and we will mention that later when we come to uncertainties. However, we have this resonance peak here. For transversal plasmons, the resonance condition looks a bit different. So there, the mass of the axion has to be equal to the plasma frequency to get resonance. Now, as I said earlier, we are considering only ultra-relativistic axion, and we assume the mass to be much smaller than the KV scale and also smaller than hundreds of electron volts. So in our result, we don't see this resonance. However, the non-resonant contributions are dominated by these transversal modes, and this is what you see here in purple. So there's a much wider continuous contribution from these non-resonant transversal plasmons. What is interesting here is that the rate of non-resonant plasmon conversion becomes proportional to the total scattering rate. And so far, this has mostly been approximated by the Roseland, by using the Roseland mean opacity. So the total scattering rate was not seen as frequency dependent. But what we're suggesting here is to use detailed monochromatic opacities and actually use a frequency-dependent total scattering rate. And this gives us a significantly different result than previous works, which is the dotted line here. This is especially larger at smaller energies. So this is actually one of the few things that we did differently compared to previous calculations of solar axion flux contributions. But let me continue with the other ones. So the Compton process, as well as Bremsstrahlung on ions and electrons, we can use again results by Georg Raffelt. And then finally the atomic transitions. These are especially relevant for heavy elements. Here we use an approach by Javier Redondo, who related the emission of axions to the emission of photons. And once we have done that, we can employ opacity calculations. So what that means is that when we assume non-relativistic electrons, which is very reasonable, but also separability of spin and spatial wave function, and we do a leading order multiple expansion of transition amplitudes, then the production rate of axions over the production rate of photons takes this very simple ratio. So this is just a simple frequency dependent ratio. And now the production rate of photons is actually very well known because it is important for solar modeling and especially for radiative energy transport inside the sun. And this is why large efforts were made to calculate these rates, and this is what people then call these opacity codes. So there's, for instance, the opacity project which put a lot of effort into detailed modeling of the different atomic transition lines of all the elements relevant inside the sun. And we can use their data and from that compute the axion production. So that is a very handy and very powerful way of including a lot of effects without calculating them yourself. Now I can already give an overview of some of the uncertainties that we have considered. I've not been in the solar models yet. Sebastian will do that in a minute. But apart from that, we are listing all the corrections here to the different fluxes. And we give a the average uncertainty. Average means average in frequency. So for helioscope, for instance, the frequency range that would be interesting is of the order from 1 kV to 10 kV. And we give here the average uncertainty over this frequency range. But also at specific energies, the uncertainty can be much larger because there might be some effect at some special point. What we see here, unfortunately, we don't have time to get into detail into all of these effects. But what we can see immediately is that the pre-Markov flux is actually already calculated to a high level of accuracy. So for a given solar model, we think we can compute the pre-Markov flux to percent level accuracy. For the plasmon conversion, the dominant effect is the one I mentioned earlier, which is the solar magnetic field strength. So in the radiative zone, the ranges that people give for the viable magnetic field differs by a factor of 15. And since it enters the flux squared, we get this factor of 225 difference. So that's a huge one. But the total scattering rate can also play a role here. As I mentioned, we can evaluate it frequency dependently or take the Rosen mean, and then we get a factor of 2 actually in the total averaged power. Now also for the ABC flux, there are some significant uncertainties that arise from the assumption that went into the calculation with the opacity, using the opacity. So there are some limitations of using this approach. And also the opacity itself has some uncertainty, of course, that then also plays a role. And the opacity uncertainty as specific energies, especially at the transition energies of in the nuclei, can be very large. So we don't know exactly how easy it is to excite these atomic transitions. Okay, but apart from that, we see that at a couple of percent, we can also predict the ABC flux relatively well. And Sebastian will now take over and tell you a bit about the solar models and how we modeled those uncertainties.
Yeah, that's right. Thank you, Lennart. So yeah, basically, as Lennart said, I'm going to dig a bit deeper into the different statistical and systematic sources of uncertainties, starting with the systematic ones. I think Lennart already gave a good overview of the of what we did for the theoretical calculations and what we found there. But basically, I mean, you can find, of course, the details in the paper, but maybe a few important numbers. So for the solar models part, we find that on average, we have about 5%, give or take, systematic uncertainties across all energies, which can be a bit higher for specific energies. And basically, if you look at the ABC flux, then we can find here, differences of up to say 20% or so. In turn, if you look at the opacity code, which is in the next element on the slide, it's basically a bit more inhomogeneous, the picture. Basically, we have uncertainties of a few percent. I mean, I'm quoting here 1.5% across the different energies. But yeah, the number can be a bit higher, depending on what energy intervals you choose. And as a sort of consequence of this strong dependence on on the energy, the differences can be really extreme for different opacity codes, so up to 400 something percent. So massive differences if you use different opacity codes. And well, I mean, basically discussion of why this is was, Javier Redondo started this discussion, gave already a good overview of this in his paper, but yeah, this would be a talk by itself to go into detail here. So what I'm going to focus on now are the solar models. So on the next slide, you will see an overview of all the models that we consider. So these are all the public solar models that we could find. If you know of any others that we might have missed, then please let us know. But yeah, to our knowledge, these are all the publicly available solar models. And what you can do is, so here they are sorted by publication date roughly. But what you can do is you can categorize them in different categories. And one of them is if they are tracking the abundances of individual elements, or if they only go up to a certain element, and then can track basically the elemental abundances in bulk, so as a sort of sum or average, if you will. And you can see that for the older models, that was still the case, that basically the older models don't really track as many elements as the later ones. And then there's another point which you can make to distinguish these models, which comes from different measurements. So one are the helioseismological measurements of the sun, basically the, if you simplified pictures is talking about some vibrational modes, observing vibrational modes of the sun. And then there are also photospheric measurements. And each of these solar models is inspired by one of these types of measurements. And as you can see, there is no model that that does both explain the helioseismology and the photospheric measurements. And that is because of what is known as the solar abundance or solar metallicity problem, in that, these observations seem to point to slightly different overall metallicity in the sun. And therefore, one thing that we need to keep in mind, and what we do later on, and what we show later on in our analysis, is that we have to pick one representative type of each class of solar models because of this difference. And also we will see how this can be used to study the models. And then the other point is basically that because some of them don't track all of the individual abundances, they're not as suited for doing axion research as the later models. In fact, I mean, some of these BP models have been used in older CAST publications. And to see this a bit more clearly, I guess, in a picture, on the next slide, what we are showing is just I guess, a broad overview of all the different interactions that Lennart talked about. So we have the LP and the TP, so the longitudinal and the transverse plasmon interactions, the Primakov, which is labeled with the P here, and the ABC fluxes for all the different solar models. And I mean, there's of course a very busy graph and showing the axion flux as a function of energy or frequency. But one of the key differences here that I highlighted with this arrow and this bar is that you see this offset between the different ABC fluxes, between the new and the older models. And also you can see that clearly that the peaks are missing. This is entirely due to the fact that these models don't track all of the elements as well, not as many as the newer ones, in particular some prominent peaks like the iron peak, which can be very interesting for studying solar properties and solar metallicity if you can detect an axion, as Lennart mentioned at the beginning. And you can see that this basically leads to an under-prediction of the ABC flux if you don't include them as well. So that's another side effect, and also a small over-prediction of the Primakov flux, but arguably that's a much smaller effect. And so maybe taking a step back on the next slide, I mean, I'm going to explicitly say what we did in terms of our methodology, and then also how this turns into estimates or the statistical uncertainties. So for the solar models, we were lucky that basically Aldo Zarinelli and collaborators in this reference given here have calculated, have done a Monte Carlo simulation for with about 10,000 solar models for each of the representative types of solar models that I talked about. And basically this is perfectly suited for our task, because this allows us to really properly propagate all the model uncertainty of solar modeling and all the correlations into our errors on the flux, because otherwise there would have been a very sort of, well, tedious and a bit, also not very precise way of, you would have had to basically assume uncorrelated errors or try to figure out the correlation between the errors of the different metallicities or the different solar element abundances. And that would have been, a very imprecise and also tedious task. So this was great. Basically, thanks to our dedicated code, as I will get to in a minute, this also wasn't too, it doesn't take too long to calculate these. So so that's basically very straightforward once you have these Monte Carlo simulations. So that was simple. For the opacities, it's not, for the opacity code, it's not that simple, because you don't really have that sort of information available, unfortunately. And so we basically had to make an assumption, which is similar to what is, or which is the same as has been made in the literature before, which is to vary the opacity like an average opacity, like the Roseland opacity. And there we use basically estimates from the literature, which we can then fully propagate within our Monte Carlo regime. And this basically leads us to the results, which I'm just briefly going to show here. So on the left-hand side, you can see the strength of the Primakov versus the ABC flux. So the higher this number is on the vertical axis on this 2D plot, the more the Primakov flux dominates. And this is of course important, because depending on which process dominates in terms of axion production. So as you know, for some axion models, for example, for the KSVZ models, the Primakov flux will dominate. Basically, you can see that you have typical errors between 1 and 5%, and they dominate in energy, sort of at specific energies for the ABC flux, which is exactly what we've seen before, these peaks. And there you have larger relative errors. And on the right-hand side, you can basically see the same, that the errors sort of become constant once one of the two processes dominates. And we've sort of classified this with a function gamma that you can, or a factor gamma that you can see in the paper. But basically, just for simplicity, I've omitted this here for this plot. And then very similarly on the next figure, just to maybe give a bit more of an intuitive feel of what we did. So here you can see a very similar thing. So again, on the horizontal axis, you can see energy. And then you can see flux, the flux relative to the AGSS09, which is one of the two representative models. So the other one being the GS98 model. And this plot illustrates lots of things. So for example, here you can see the gray lines, which are just some random Monte Carlo samples, which kind of give you an idea how we determine the mean or the median values. I mean, the distributions are actually fairly symmetric, so it doesn't really matter if you take the mean or median, and also the uncertainties. And speaking of the mean, on the left-hand side, you see the Primakov flux, on the right-hand side, the ABC flux. And what I want to just highlight here again is you can highlight the difference between the means. And this is basically just due to the solar metallicity problem, or this difference in these models. It's kind of, this sort of systematic effect, if you will. And then, of course, the other thing you can highlight are the statistical uncertainties, which you can very simply estimate by estimating the standard deviation from the Monte Carlo samples. You could also estimate intervals, but again, the distributions are fairly symmetric and very well behaved. So that's a plus in that sense. Right. So before I'm going to hand over to Lennart, just I guess two more slides on our code. So just a brief overview. So our code is a first principles calculation, as Lennart pointed out, it's still fairly fast, despite being first principles based. It's a C++ library with a very simple, for now at least, Python frontend. I mean, if people find this helpful, then yeah, we will definitely consider expanding this. But the main intention for now was to just basically allow people to reproduce more or less what we did without much of a problem. And in fact, it should be very simple to install this code because it doesn't depend on anything complicated, like, for example, root or anything. So yeah, my invitation is just to basically download and try it. You can find the link in the paper and also here. And yeah, just to give you a very brief overview or very brief example of the code of the Python front, it's fairly straightforward. You just basically import, once you install, download and install the code, you just import the module. You can use your usual Python help function or anything like that on a module to analyze its constants. Then there's a what I at least think, very handy function, which is a test module function, which basically runs a few test functions, takes a couple of minutes, up to 10 minutes or so. And you can see basically the underlying C++ file basically is a good, I think, starting point for those who like to intuitively approach a code. And then also, I think, fairly intuitively, you basically pick a few radii, energy values, solar model, some random output file, root name, and then it will calculate in a very short time, for example, the Primakov interactions for the spectra, and will sort of also adjust, as you can see here with this rounding. This is not, so the radius was chosen as 1, but some solar models basically don't provide the information up to the full solar radius. But yeah, anyway, so I think this is a fairly straightforward way to do this. And so yeah, I think for the last few minutes, Lennart will talk about what else you can do with this code.
Yeah. So because as we promised, we also wanted to have a look at whether we can actually distinguish different QCD axion models, taking into account all of the uncertainties that we have discussed. So systematic uncertainties of the calculation, systematic uncertainties of solar models, so this high versus low metallicity discussion, as well as statistical uncertainties of the measurements that enter the solar models. So let's have a look at this. We've seen that the Primakov flux is more precise, so we will stick with the Primakov flux for this example. So we're supposing that we're either detecting nothing or that we detect a Primakov flux. As we've seen, the spectra look very different from ABC flux to Primakov flux, so it's rather easy to distinguish the two, but we want to go further than that. So first of all, the uncertainties affect bounds that helioscope set on the axion-to-photon coupling only very weakly. So the helioscopes get a signal, so the number of detected X-rays per time is proportional to the coupling to photons to the power of 4. And the uncertainty from solar models, as we've seen, and then also the systematic uncertainties are a couple of percent. So I think none of these bounds actually claim to have precision level accuracy. So nothing really changes there. But if a signal is detected, we actually don't measure the coupling to photons as we want to, but we actually measure something different, which is some constant times the coupling of photons. And this constant is the power, could be seen as the y-axis here, is a solar property. So how well does our solar model produce axions? And we see the higher metallicity solar models produce more axions, and so therefore have a larger value of this C here. And what then is also very clear is that there's a generous C between C and the axion-to-photon coupling. So whenever we see some signal and let's say we have a high metallicity solar model, we could explain the same signal with a low metallicity solar model and a slightly stronger axion coupling. So we essentially measure this product and not just the coupling itself. However, this can be circumvented because some, or at least the favored QCD axion models, do not have continuous values of the axion to photon coupling. This is because this coupling is generated by an anomaly, and this ratio here, the axion to photon coupling over the mass, actually takes discrete values that is given by the ratio of anomaly coefficients minus some model independent contribution, which is this 1.93. There have been some studies into what preferred models should look like, and there are cosmological arguments that the additional quark content should be unstable, and that there shouldn't be Landau poles below the Planck scale and so on. So there are a couple of arguments by which we sought preferred models, and this is what has been called the axion window by the authors of these two papers that I list here. So when we take just the QCD axion models into account that lie in this axion window and plot this in the parameter space that is interesting for helioscopes such as the International Axion Observatory, which is, as I said, being built at the moment and will hopefully be upgraded in the future. Then we put the mass here on the x-axis and the coupling to photons on the y-axis, the cast limit, which is the strongest current limit, and the predicted sensitivity of the IAXO experiment. And now these purple lines are different QCD axion models that lie within the this axion window. So those are the ones that are theoretically preferred. And to check whether IAXO can actually distinguish all of these different models, we take some exemplary values. So each of these crosses is a possible axion. So suppose the axion sits here with this mass and this coupling to photons. Then we can calculate for each case the 95% confidence interval, which is then this shaded gray area here. So what we see immediately when the axion is too light, such that we can't really make a mass measurement, the IAXO cannot distinguish it from a massless axion, then we can't pin it down to any of these lines, but instead the confidence interval crosses many of these different models. But as soon as the mass gets larger or the signal gets stronger because we have a stronger coupling to photons, then this starts to change. Here, for instance, we already pin it down on two different values of E over n. So this observation that we show here would already be a very strong constraint on UV completion of such a QCD axion. And this gets better and more precise the stronger the signal gets. So here it's just on one line, and for these A, B, C, and D cases that we labeled here, the confidence interval is so tiny that we can't really see it here. So we provided some zooms, and we see that for C, this is very clear that we would suggest a specific value of E over n. What also becomes visible in these zooms is that these high metallicity and low metallicity solar models, so high and Z, these are the red and the blue bands, and only the overlap appeared purple on the left here. These might also become distinguishable because, as we mentioned, we're not measuring the coupling to photons, but we're measuring the ability of the solar model to produce axions times the coupling to photons. And when we restrict ourselves to these discrete values, in some optimal cases, like in the case A, the observation can really only be explained by a higher metallicity solar model together with this specific value of E over n. And therefore, there is a possibility to do some axion astronomy and to get a hint. I would not call it more than a hint, but to get a hint towards whether the metallicity in the core of the sun is actually better described by high metallicity or by low metallicity solar models. However, we have to keep in mind, and that's what is illustrated here in the panel B, that we don't know for sure that the detected axion has to be in this axion window and be on one of these lines. So of course, it's still possible to detect it somewhere else. And there are models for this, which, for instance, contain a very large and complex additional particle, so have a large additional particle content, and then we can generate very different values of E over N. Yeah, there will always be someone to cook up a model that lies somewhere else. That is for sure. However, the more simple models can definitely be distinguished. Now, to conclude, we reviewed the solar axion flux calculation, and we focused on its uncertainties, and we've seen that the Primakov flux is already predicted at a very high level of precision, and that the ABC flux is actually affected by much larger uncertainties. To improve the precision, one could do a dedicated plasma simulation and including the axion emission. This would be something like an axion luminosity project, but this is probably equally difficult as doing one of these opacity calculations. So yeah, that's not entirely easy to do. But in addition, we would also be interested to get better QCD and calculations and or measurements to get this ratio of the coupling to photons over the mass more precisely. We also developed a library for axion flux calculations. I give you the link here once again. And this is compatible with many solar models and several opacity codes. So you can use it as soon as you're interested in some solar model experiment. And it might also help to estimate systematic uncertainties for a specific analysis, because you can always run your analysis with different solar models. And finally, we showed one example what you can do when you take care of all of the different uncertainties, which is that we can really argue that the IAXO can distinguish different QCD axion models in the axion window, but that is only if a mass measurement is possible, because otherwise the certainty interval will always cover many models. And also in some optimal cases, when we have a very strong signal, it might actually be possible with the IAXO to get a hint towards higher or low metallicity solar models. So that is a very interesting prospect as well. And with that, I think we're finished, and thank you very much for your attention.